All right. So last time we talked about a comparator. We talked about numbers. Today, we're going to deal with this. That's as hard as it gets today. What is that? It's an AND gate. What are the inputs? What do we normally call the inputs of an AND gate? A and B, X and Y. Today, I'm going to call it A. Nope. And enable. EN, enable. So let's look at the truth table for this new gate. Woohoo. A and enable. I lied. Do it the other way. Enable and A. 0, 0, 1, 1, 0, 1, 0, 1. So 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. And of course it's behind my face. There's nothing really earth-shattering here. Okay. But what if we look at when enable is 0? When enable is 0, what's the output? 0. When enable is 1, what happens to the output? It's equal to A. We call this, especially if we can use a pen, the enabling function. If AND is the enabling function, then obviously NAND is not an enabler. That's a joke. You've had too much. Friends don't let friends make jokes this early in the morning without coffee. All right, never mind. It's the enabling function. So the enabling function says A, if enable is equal to 1, else 0. Everything good there? So what I'm going to do is I'm going to start by building up a pretty basic kind of gate. Well, actually, hold on, I want to show you one more thing. Gate, inverter, enable, A. What does the truth table for this guy look like? Again, enable and A, 0, 0, 0, 1, 1, 0, 1, 1. Well, whenever enable is 1, that means over here it's going to be 0. So automatically I know that those two rows are going to be 0. If it's 0, then I know that this is going to be 1. So this is 0, 1. So again now, when it is 1, I've got 0. When it's 0, I get A. So this is a different kind of enabling function. And we would usually call this an active low enable. Enable. It's an active low enable, meaning when the enable is low, we're actually doing something. When it's low, we're passing stuff through. As opposed to this enable function, which is an active high. When enable is high, we are enabling A to pass through. So enable acts as kind of a gatekeeper. Either A goes through or it gets set to 0. Now, let's for a moment continue on with very complicated circuits. A. What is the output of that function? That's A. All right, well, let's add some complexity. This is one input, two outputs. What's this second output? A naught. Okay, let's combine those now. Those two circuits. Enable, going to both of them. And then here is my new complicated circuit, A. This is a case of two inputs, two outputs. So to build this, we've got enable and A, 0, 0, 0, 1, 1, 0, 1, 1. And let's call this guy D sub 0 and D sub 1. So, what happens when A is 0 and enable is 0? What is the output for D0? What is the output for D1? Let's concentrate just on D0 for a second. D0 relies on enable and A bar. A bar is 1. So what is 1 ANDed with 0? 0. And what is 0 ANDed with 0? 0, fine. Okay, then the next case is enable is still 0, but A has changed. A is now 1, which makes that 0. So this is 0 and 0. This is 1 and 0. So that's 0 and 0. Which makes sense, right? We know that the enabling function is just always going to be 0 anytime enable is 0. When enable is 1, that's when interesting stuff starts to happen. When enable is 1, that means that this might as well just pass this input straight through. So now enable is 1 in these last two rows. So D1, if we follow it through, right? D1 is just going to be A. So it's 0 and 1. What about D0? What's D0 going to be? It's going to be A bar. So that's 1, 0. This is the start of a device called a decoder. Now this by itself is what we call a 1, 2, 2 decoder. This device below that I wanted to circle in red is what we call a 1, 2, 2 with enable. And if you have enable, it's much nicer to be able to build larger devices. But that's the basic idea. And we can combine small decoders to make larger decoders. All decoders activate one of 2 to the n outputs based on n select lines. So there will always be some number 2 to the n outputs. It will activate one of them. There will be n select lines that tell you what they are. Outputs should always be labeled, for the sake of this class, are labeled D0 through Dn to the minus 1. Sometimes they're labeled Y0 to Yn minus 1. There are n select lines. If there are n select line and 2 to the n outputs, that's something like 2 inputs, 4 outputs, 3 inputs, 8 outputs, 4 inputs, 16 outputs. It's a number and it's a power of 2. If the select lines usually S how do I do that? Have I done something silly? Nope, I have not. Yeah, I did do something silly. All right, the way I put this is 1 to 2 to the n. So this would be 4, 8, 16. So I really should have put 2 to the n minus 1 here. And the select lines are n down to S0, n minus 1 down to S0. A quick picture, I think, will solve all this really easily. If you have a generic decoder with, say, 3 inputs, that'll be S2, S1, S0, and then you'll have 8 outputs labeled D0 through D7. So, many outputs, a few inputs. So if the select lines are red in binary with S n to the minus 1 as the most significant bit, that D output is activated. The idea is if S is equal to 1, 0, 0, then D sub 4 is active. Is everybody okay with that? You basically can just read off the select line numbers, and that's what you get for an output. What I have not mentioned here is the use of an enable. So one more caveat. Rather than take up a whole page with that one thing, I'll just say right here. Come on, move. Thank you. If enable is 0, I shouldn't say 0 either. I should say inactive. All outputs are inactive. So I said what I originally wrote was if enable is 0, and that's not really accurate. If enable is inactive, because as we just talked about with that enabling function, we have the idea of an active low enable. So active means if it's low, then stuff passes through, whereas active high says if it's a 1, stuff passes through. Everything we've done up until now has been active high logic. Now we're entering into this idea that maybe we want things to be active low logic. So I've replaced a lot of the words where I would normally say 0 or 1 with active and inactive. Let's just look at those real fast. So an output will be activated. The enable is activated. And then the outputs are active again. So when we have items that we want to think of as active low logic, here's a picture of a decoder. We haven't built this decoder yet, but we will. S1, S0, enable, 1, 2, 3, 4 outputs, D1, D0, D1, D2, D3. All of these right now are what we call active high. Active high means this is going to be enabled if you put a 1 in. So these are active high. Which is the default. The default is active high. Also, all of the outputs are active high. Remember, the idea of a decoder is only one will be active at any time. So only one of these will be active. 0, 1, 0, 0 is a perfectly valid output. How would I get this output? Based on the English definition of a decoder, what would I have to put on the select lines to get D1 to be active?
You need a 0 on S1 and a 1 on S0.
A 0 on S1, a 1 on S0. Yeah, if you read it in binary, that's 0, 1. So it outputs D1. If I wanted 3, I would put 1, 1, because that's 3. This is 1. Okay. That's active high. I know I've got a title that says active low, so let's do this. Put that over there. All of this is active high. Active low is almost the same. Same device, 2 inputs, an enable, 1, 2, 3, 4 outputs. But if we're going to say that things are active low, we put a bubble on it. What is the bubble indicative of? Well, it's indicative of an inverter. Okay. So this says, hey, this is an active low enable. So now 0 will actually cause this to be enabled. Furthermore, if we wanted to, you don't have to be all or nothing. It could just be the enable is active low. Frequently it is. But you might also want to have, or maybe just have, the outputs active low. Now remember, only one thing can be active. And if it's active low, that means only one thing is going to be low. The rest will be 0. S1, S0, D0, D1, D2, D3. It's always important to label these hierarchical diagrams. Okay, so active high and active low are nothing more than adding in a bubble. And when you're talking about active low things, it helps to keep in mind the English definition. Enable is active low. Things will only be happening if the input to enable is low. If it's active high, things are only happening if the input is 1. So there's a good definition of both active high and low outputs, and active low and active high inputs. All right. So we have built up, what have we built up? We've built up a 1 to 2 decoder. The 2 decoders that we've built that are 1 to 2, one of them looks like this, S0, D0, D1. The other one looks like this, S0 enable, D0, D1. The only difference is with the one on the left, something is always going to be active. There's no way to disable everything. More frequently, we want something with an enable so that we can turn it off. Okay? Now, how do you build up from a single bit to multiple bits? This is the same problem we faced last class. So what we're going to start with is, let's look at just a smaller case, a little bit bigger than this, but not really big, and see if we can build it monolithically. So for a 2 to 4, S1, S0, D0, D1, D2, D3. Let's not deal with the enable just yet. Let's just deal with this. Our truth table is S1, S0. We have 4 outputs, but this actually is a pretty simple diagram, all right? D0, D1, D2, D3. Okay? It doesn't matter how many outputs we have because we only have 4 input combinations. So when the binary of S reads 0, that'll be active, and everything else will be inactive. When S is 1, D1 will be active, and everything else will be inactive. When it reads 2, D2 will be active, and everything else is inactive. And when it's 3, D3 is active. Everything else is inactive. So how do we build this? Well, I mean, we're looking at this. It's pretty obvious what's going on here. D3 is just S1 ANDed with S0. D2, well, D2 is S1 and S0 not. So as we get into more complicated things, we don't have time to draw as much. So now, instead of drawing a full inverter, I'm just going to show that the AND gate has an inverted input there by drawing a bubble. D1, well, that's just the opposite. That's S1 bar S0. And finally, D0 is only true if both S0 and S1 are false. So to build this, we need to have access to both S0 and S0 bar and S1 and S1 bar. So how would we actually get that? Well, if over here we had our S0 and over here we had our S1, I know that S1 has to go to the following places. There and there. I know that S0 has to go to the following places. S0 goes there and there. Then what do I need? I need S0 bar. So S0 bar, I can throw an inverter right there. And S0 bar goes over here. And where else does it go? Here. And finally, what color do I have left? Yellow. S1 bar. I need S1 bar. Put an inverter in here. S1 bar needs to go, well, right there. And also right here. Now, this is building it just fine, right? If I erase those lines and just connect them up, there it is. My inverters are on the left, and everything is hunky-dory. Blue, blue, green, green, and yellow, yellow. But hang on a moment, because I see something interesting here. I see that. And that's interesting because I just saw that a second ago. What are these devices that I've built? This inverter. This is a 1 to 2 decoder. 1, 2 decoder. So automatically I can see that to build this 2 to 4 decoder, I can use 1 to 2 decoders. And then what do we have over here? What do we have over here? We've got some AND gates. What else did we say that AND gates were? We said that AND gates could be used as enabling functions. Okay? Each one of these AND gates acts as an enable. Okay? So if both of the inputs are 0, for example, we set this guy to a 1. So let's build this now using some block diagrams. We said this is how we use 1 to 2 decoders. So here we've got a 1 to 2 decoder with S0. We've got another one with S1. And then over here we had a bunch of AND gates. And we said, all right, if both of them are 0, D0 gets activated. If S0 is 1 and and S1 is 0, that's D1. Otherwise, the last two, both of those have to be 1. And then here we say 0. And here we say 1. Yes, this is a terrible schematic. You should always make it nicer than this, but I'm trying to show direct lines with only one color, D2, D3. Well, this doesn't really help us because if we try to build it more than this, we're just going to end up with a bunch of AND gates on the end. But let's go back and look at this one more time. Let's just look at the top half. That is not the right color. I wanted this color. Okay, here's the top half, and here's the inputs for the top half. Notice, what is this yellow line acting as? Follow the yellow line back. Here it is. It's just going off. Both AND gates have an input that comes from the same item. Look at the bottom 1 to 2 decoder. The bottom 1 to 2 decoder also has an AND gate. It has an AND gate also. So what we actually have here, we started by drawing a 1 to 2 decoder, but what we really have is a 1 to 2 decoder with enable. So redrawing this a little bit more now. Next page. Thank you. We've got S0. Actually, move this over a little bit. We've got S0. We've got S1. So I'm going to be doing a few interesting things here. So here's S0. S0 comes through, and it touches D0 and D1. Now D2 and D3 also have a little bit to do with S0. You can follow it back, right? Where did it go? I've made a mistake. I've made a terrible mistake. That was supposed to go a little bit further. There we go. Okay, so both D0, D1, and D2, D3 actually are affected by S0. So let's throw that in there. Let's say that. All right. D0, D1, D2, D3. But if we add in the idea of an enable, what would the enable be? For this first part, we saw that the enable, highlighter, the enable comes from the D0 output of S1. What about the enable for D2 and D3? That enable comes from the D1 input. So that's exactly what I'm going to do here. I'm going to bring the enable out like so. And we can throw an enable on that as well. So here we have 1 to 2 decoders, 3 of them. Let's go through a few examples here of S1 and S0 and see what happens. 0, 0, 0, 1, 1, 0, 1, 1. So here I'm going to use green to indicate that something is a 1 and red to indicate that something is a 0. So we start off 0 on the input, and 0 on both of these inputs. Which one of the, assuming that enable is high, which one of the outputs here are going to be active? D0 or D1? D0 is active, and D1 is inactive. Now, what does it mean if something is inactive on the bottom one? What are the outputs automatically going to be? They're both 0. This is green, though, so which one of these is going to be active? D0. D0 will be active, and therefore D1 will be inactive. Now, is that correct? Only D0 is active here, which is exactly what we expect. We put a 0 in, we get D0 active. All right, we can redo this as many times as you want. Let's pick this one here. So S1, and of course now I can't erase all of this, so let's just make them black again. Okay. So enable is high, and we put in a 1, 0, 0. So this is going to be, oh no, not this one. This one is now going to be active. This one will be inactive, which means both of these are 0. And we've put in 0 here. So this one will be active, and that one will be inactive. Here's where people tend to get confused. Yes, I wrote D0, D1, D2, D3 here. But each one of these has a D0 and a D1 and a D0 and a D1. And here, D0 and D1 connect to each other. Here, D0 connects to D2 and D1 connects to D3. So you have to be able to keep those straight in your mind as you're doing this. But building up any size decoder can always be done with 1 to 2 decoders and then built up from there. So generically, we have the following device. N inputs, 2 to the N outputs, and possibly an enable. Okay. To build up any size decoder, start at the outputs and place decoders until you have the needed number of outputs. So if you're using 1 to 2 decoders and you need to build a 3 to 8 decoder, you're going to place 4 1 to 2 decoders because there'll be 2 outputs on each of the 4 for a total of 8. Done. If you're building a 16 out of 2 to 4 decoders, so 4 to 16 out of 2 to 4 decoders, you still need 4 because it's 4 plus 4 plus 4 plus 4 is 16. So whatever you're using, that's what you need. Then you're going to step 1. Step 2, move to the left. All enables are now, quote, outputs repeat step 1 until you have one enable. So if you were building a 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, out of 2 to 4 decoders, you would need 4 2 to 4 decoders. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Each of those has an enable line. If you then wanted to use 1 to 2 decoders, you would use 2 of them because they have 2 outputs. Then here you have 2 enables, so you have to use a 1 to 2 decoder. And now you have just 1 enable, so you're done. The next step, step 3, apply select lines in parallel with the most significant bit on the left under my face. I don't know if I can fix that. There's here. Okay. Apply the in parallel to the left. Left. What does that mean? Well, that means that the 4 to 16 decoder has 4 select lines. 4 to 16 has to have 4 select lines. So those are S3, S2, S1, and S0. So starting on the left, you use the most significant bits. This has, let's label what select lines we have. Here there are 2 select lines on each of these. So in the first column, we apply S3. In the second column, we apply S2 in parallel. So both of the decoders. Why aren't you being useful? There we go. Both of the decoders get S2. In the next stage to the right, there are 2 select lines. So we apply S1 and S0 in parallel to both. Okay. To do lab on Wednesday, we need a slightly different kind of device. This goes from a small number of inputs to a large number of outputs. We're going to be using a device called a multiplexer, which goes from many inputs to 1 output. Now, you have all the tools you need to build this already. You don't have to build it, you just have to use it. Notice that we have the same sort of setup. We've got something that looks kind of like a 1 output. We've got 2 to the n inputs. We have n select lines. Okay. Now, the problem you're going to be faced with is you're going to be given a bunch of 8 to 1 multiplexers. 8 inputs, 1 output. You choose which of the inputs get sent to the output. It's almost the exact reverse of a decoder. Here you choose which output gets activated based on some number of select lines. Here you choose what input gets directed to the output based on some select lines. You're going to be using 8 to 1 muxes, but the truth table that you're going to have is 16 rows long. So what I want you to do is you're going to have Z, Y, X, W as your variables. What I want you to do for S2, S1, S0 is I want you to hook up Z, Y, and X. Now if you do that, just look at the first 2 rows of the truth table. Those are how we would set up a truth table, right? 0, 0, 0, 0, 0, 0, 0, 1. Well, that means that this right here, when you put in 0, 0, 0 for z, y, and x, this has to give you the answer y for not y, f, for both w equals 0 and w equal to 1. So if it's 0, that's actually not a function of w. It's just tied low. In fact, we can look at all of the possible combinations for w, 0, 1. It could be 0, 0, could be 0, 1, could be 1, 0, could be 1, 1. And actually, you know how to solve all of these equations. 0 is false. You just tie it to ground. We would say tie to ground. 1, 1 is just always true. You would tie it high. What happens if you put in a 0, you get out a 0, you put in a 1, you get out a 1? What function is that? Well, it's just a wire. It's just W. You just have to hook up W to one of those inputs. What about if you put in a 0, you get out a 1, you put in a 1, you get out a 0? It's not W. So in fact, when you build your truth table, it's going to be this simple. Okay, just rely on the fact that you hook those up that way. Z is the most significant bit. X is the least significant select line. W is the least significant bit of your truth table. And then you can just look and say, hey, it's either 0, 0 or 0, 1 or 1, 0 or 1, 1. And that's how you design this. The only hard part is you need to design this 4 times, because there are 4 different circuits, using 4 different 8-to-1 muxes. And if you, we'll do it this way. I'll leave you with this. If you are like your TAs and lazy, yes, I'm making fun of the TAs. They had to do this as a pre-lab for me last week, 2 weeks ago, and they just wanted to get it done. Here it is. That was what they designed. Do you know what they didn't do beforehand? No fritzing. So it looks like shit. It also, all right, and here's the real thing, okay? This was their design. I went over and I pulled out that blue wire. And I said, go ahead and fix it. And they just kind of cried. And that's a problem, because I'm not going to come over to you and be some kind of a jackass, pull out a wire. But you're going to suddenly turn to your friend and you're going to, oh no, some wire came out. You're not even going to know what wire it was. But if you have your fritzing schematic, you'll be able to deal with that. So I highly encourage that you take all of those skills that some of you grabbed on Friday and apply those to the lab. Start today. All right, there's a reason I don't give much homework, because the labs should be more than enough work for you.